Well, I was always interested in math as a young person, but my interest really manifested itself in the selections that I made going into college. I thought initially I wanted to go into industrial engineering. They didn't really have a program where I was, so I thought, well, maybe chemical engineering. And it turns out I didn't really like the lab work, and so I ended up in electrical engineering, which was heavily invested in math to really understand and do it well. And so I got my undergraduate degrees in electrical engineering at City College in New York, and then master's and PhD in electrical engineering at Princeton University. I was not really into computing at that time. I mean, I did some playing around with some of the early elemental computers, flipping toggle switches and the like. But at some point along the way, I joined the faculty at MIT and took a leave of absence to get some practical experience because I was mainly more theoretically oriented at that time. And I went to a consulting firm in the Boston area. It was in Cambridge called Bohl, and Newman. And they were getting very interested in computers. They started out dealing with acoustics, one sort or another. A lot of the folks there were faculty members at either Harvard or MIT. And there was a small group of folks there that were interested in computing. I was not one of them. I think they hired me maybe because of some interest in networking that they might have. But I started to learn about it while I was there, and we were so successful in the networking side of things that I eventually got offered to come into DARPA, and I ended up running the office there that funded all that computer research. So by the time I left DARPA, which was in late 1985, I was pretty well immersed in the whole computer science field big time. In the early 1970s, we were still mainly in the era of big time sharing systems. So most of the universities had big mainframes. The universities had, mainframes. You'd submit decks of cards with punched instructions. They give you a printout the next day, and there had been a lot of effort on DARPA's part to move things toward time-sharing systems where you could do interactive programming with the machines, and they could give you results right then, and if there was a bug, you could fix it right then. And so I began to see that when I was at DARPA. In fact, ISI ran most of the interactive computing for DARPA out in the Los Angeles area. So we would use the ARPANET, which was now functioning at that time, to access those machines. That was probably the biggest change, namely the introduction of networking and the introduction of time sharing. And not too long after that, we got into the introduction of personal computers and the like. And that, of course, has radically changed. That plus the internet has radically changed what we saw in the 80s and early 90s. And then, of course, the introduction of the whole cell phone and smartphone arena, wireless arena, has made it sort of ubiquitous. You can now carry that much computing in a shirt pocket. In the early 1960s, we were already in the wake of the Soviet launch of Sputnik. DARPA responded to that, or DARPA was the response to that in some ways. The U.S. had the capability to do it, but nobody had the responsibility. So DARPA was set up by Eisenhower as a means for the U.S. to maintain a vigil over technology and basically keep eyes open for high-impact, maybe high-risk, high-impact technologies like that was. So DARPA was set up in 1958, I believe. When I went to DARPA, I joined an office that was set up to deal with information processing, which was mainly computing. But people could see the need for networking at the time, if not just to link computers. And from a DARPA perspective, it was a research project, sort of how could computers interact with each other in interesting ways? Because people do that all the time, and maybe computers could do it in interesting ways. But from a defense point of view, there were all kinds of command and control related motivations for doing that. The military might be able to use it to, control battlefield operations and the like. So there were the mix of things going on. The research community was really challenged to make networking happen. DARPA put out a request for quotations for somebody to build an initial 4-node network. I had just joined BB&N at the time, and I had been working on networking without knowing that DARPA was even interested in the subject. So I had a stack of documents about error control, buffer control, flow control, routing, and the like. The gentleman who ran that group at BB&N was a fellow named Jerry Elkind, who later got hired back into MIT and then went out to Xerox PARC. And Jerry asked me to send those documents to DARPA. That was my first interaction with DARPA. I sent them to a fellow named Larry Roberts, who had just been hired to take over a network project that was hypothetical at the time, but they were planning it. And I got a call back from Bob Taylor, who was running the office. And he said, wanted me to come down, he wanted to meet me, and so I did. We had an interesting discussion. I ended up writing the technical part of the proposal, or I'd say 90% of it. And we actually won that competitive award. I think there were a number of other bids, including some of the big companies whose name you would recognize today. But we won it. I can't tell you what the DARPA rationale was, but I think they thought we had a good crew. I was sort of the lead designer. We had a number of people who were really expert in building real-time systems that had just joined BB&N from Lincoln Laboratory. And so they asked me to join them in actually doing the building of it because, if you don't know about the conceptual part of it, it's hard to actually know how to deal with all the ramifications that might occur. So we actually built it, and this was the first versions were deployed in 1969 out at UCLA. We had 4 nodes. The first one was in September, roughly September 1st. The next one, October 1st at SRI in the Bay Area. The third one at Santa Barbara, between the two. And then the fourth one at Utah in December. So by December that year, we had 4 of them. I did all the testing out on the West Coast to make sure it worked with a colleague of mine named Dave Walden, who came along. He was one of the programmers. And that was something that was very widely adopted within the research community pretty quickly. By the time I joined DARPA, it was clear that this technology really had application in other domains. Like it could be used for long-haul communication to ships at sea. We had colleagues in Europe that we wanted to deal with. We were trying to string wires. And the CCITT regulations made it really hard to keep stringing wires from machine to machine to machine because they required all the contributing carriers to agree. And so if one carrier back in the US was being asked to agree to a node from, let's say, London to Germany, they may say, no, why don't you take a link from the US to Germany, because it's cutting into our business. So we could clearly see that would have extension problems. And we built a packet satellite network that linked the US and European folks. We had 4 places in Europe, Italy, Germany, a Norwegian connection through the Scandinavian station. We used Intelsat 4. The other one was in England and the US. Intelsat 4 was really the only satellite we really had an option to use at the time because there were no domestic satellites at all, unless we piggybacked on the defense ones, which was a possibility. And the other one was using it for ground mobile radio. And we built a packet radio system, which was the very first one that used digital control of the radios, I believe, and it also used direct sequence spread spectrum technology, which is a way of using a wider band that you need so it would mitigate against interference. And so we made that happen when most people thought maybe it wasn't even possible. Nobody had ever done that before. And I think that became the template for what actually happened with the cellular deployments later in the 1990s. So that was what was the genesis of the International Internet, taking those 3 different nets, the satellite net, the radio net, packet radio net, and the ARPANET, and making them all work together. They're all different. And, it's lasted some 50 years to this point. I see no likelihood that it's going to go away anytime soon. I'm sure it'll get replaced by something even better once we figure out how, or somebody else figures out how. But I think it was a major contribution back in design-wise in the early 70s and deployment-wise in the early 80s. So it's one thing to design a protocol. It's another thing to document and implement it, but it's something else to deploy a whole collection of networks and machines and show that they can all work together using those protocols, which is what we actually did. And I was fortunate to have a really great collaborator in Vint Cerf in doing that. He came out of the computer science side of the field. I came out of the communication side, having started my career at Bell Labs, which was big into communications architecture. And together we kind of masterminded the deployment. We didn't do everything ourselves, to be sure, because the internet is so big and diverse. I mean, initially we had hundreds of people involved, and today I don't know how many millions are directly involved in bringing it to the public and to industry and government and universities. If you talk to Steve Crocker, he'll relate to you what he and some of his colleagues originally did on trying to build a network protocol, which assumed the network would be perfectly reliable. I'm not sure they believed that it would be perfectly reliable, but that was the assumption on which they built their protocols. As I was thinking about it later on, this would have been in the 71, 72 timeframe while I was at BB&N, I kept saying to myself, instead of making the network totally responsible, why don't we get the host computers involved in the process? If you use a radio net, you could have interference, you could be behind a mountain, you could be in a tunnel, there could be all kinds of reasons why communications could be interrupted. And you didn't always want to go back to the starting point and restart and hope that you got a perfect communications, especially for the transmission of longish messages. I actually wrote a paper back in, I think it was 1972. It was actually quoted, one of the references in Bob Metcalf's. He's the guy who did the Ethernet out of Xerox PARC with Dave Boggs. He actually had a PhD thesis on this topic, and he cited that paper that I wrote. I haven't been able to put my hands on it again. It was never published as an external report from BB. It was an internal project. But basically said we ought to get the hosts to play a role here. Let them participate in the error control and making sure that the communications is really robust. So if the network doesn't really serve 100% reliability function, the hosts can pick it up and kind of go back and get the things that we're missing and the like in a more fine-grained way. With the ARPANET, let's say you're transferring a long file from one machine to another. Let's say for the sake of argument over a 50 kilobit net, which is what the speeds were in the ARPANET, that transfer would have taken 10 or 15 minutes. Let me just hypothesize. It would be a long file. Something happened partway through. What you would have had to do is kind of stop things, go back to the beginning, and do it over again. And it didn't seem like a reasonable thing. You'd be able to, like to pick up where the errors were occurring and just pick it up from there. Keep going from that point. So that's what I was sort of outlining. This was about making the ARPANET protocols more robust by putting the responsibility in the host. But I was, in my own mind, thinking to a future time when the network that was hosting these might not be as reliable as the ARPANET was. It was pretty reliable, to be sure, just as predicted, but it wasn't perfect. I mean, nodes could go down, you could have, cuts in the system, but very unlikely and very infrequent that they would ever occur, probabilistically speaking. So when I got to DARPA, one of the very first things I did was start a project on packet radio. Second thing I did was to pick up where DARPA had been interested in a satellite link to Europe before, but the way it was planned at the time and the way the folks in Boston at BB&N had implemented it, this was after I was no longer in the process of being involved there, because I had gotten into demonstrating the ARPANET, and so I wasn't as directly involved at that time, was they were going to take the ARPANET and just add a lot more memory so they could do buffering of the satellite transmissions, but make the links basically like landline links, only over satellite. and there was no separate network there. It was just like an extension of the ARPANET. Well, there was no way to show that you could put multiple different networks together unless you had a separate net. And so what I forced to happen was to take the satellite net and cause it to have its own interface. The ARPANET had its own interface. And what I was talking about in the way of gateways to link these networks was to have the gateways be the kind of the interface between the two networks. So you can have any networks that plugged in. You just have to figure out how to plug in here and here, but the functions of the gateways would be kind of generic for any net. They have to know how to do routing in the global environment. And so, I mean, I started with that notion in mind, but it wasn't yet in a form that we had specified enough of the details to go implement it. And so Vint and I got together, sometime in the early 1973 timeframe. He remembers it slightly different than I do. My recollection is we had our first substantive discussion of this at the major network conference, which was called the NCC at the time, which was at the Statler Hilton in New York. He seems to think it happened earlier. But the bottom line is, together, we were able to figure out what a good strategy was for making that all work to the point where you could actually go out and implement the gateways. Today they call them routers. You can actually implement the protocols. And then DARPA funded both Stanford and BB&N, as well as University College London, to build the first 3 host implementations of the TCP/IP protocols. And we funded BB&N to build the first version of a gateway, which they call a router, and it was based on the use of LSI-11s, which are the small computers from digital equipment. Keith had been, I think, deputy head of an IT group at the RAND Corporation. And I had quite a number of interactions with him, during that whole period. I knew him when I was at BB&N, but that was a period where the head of his group was a fellow named Willis Ware, who ended up staying on after Keith took part of the group and left to form ISI. But the issue that they were facing at the time was the ramifications of the Pentagon Papers release. If you remember, this fellow Daniel Ellsberg had released them, which caused a strong reaction in the Pentagon. It became pretty clear to Keith, I believe, maybe to others there too, that at least for a while, likelihood of new funds to the RAND Corporation to work on advanced research were pretty slim. And Keith was feeling overly constrained. For all I know, he was looking to be number 1 in a place rather than number 2. I can't speak to that for sure, but he ended up deciding to pick that group up and move it somewhere else. I remember talking to him during that period. I made a special trip out to ISI to talk with him. And at the time I did, he said he still hadn't decided what to do. But he eventually decided to move it over to ISI. He had gotten a very good deal from the dean at the time, was Dean Caprillion. From a DARPA perspective, it looked like a very useful thing to happen because Keith was devoted to service to others. And so if he had set up ISI, we were all aware that while he would do some research on areas that were of interest to the people there and that DARPA would be willing to support it, he would also be providing support to DARPA in ways that maybe we couldn't even envision at the time. Well, it turned out later on they provided a lot of the fundamental administrative support for making the ARPANET internet happen through the work of John Postel, who later joined them. He wasn't there at the time. But they also did some really innovative research at the time. So DARPA saw it as in their interests. But it wasn't DARPA that went to Keith and said, would you do this? It was Keith who was feeling the need to branch out. One of the people that ISI hired, I would guess in either the 72 timeframe or maybe 73 timeframe, was a fellow named Danny Cohn, who at the time was on the staff at Harvard. I don't know whether he had a faculty position or was just a senior research guy there. Danny was one of the most creative folks when it came to making use of network technology. He was also interested in graphics. He had worked for Ivan Sutherland, who had been at DARPA before, and Ivan was sort of viewed as the father of computer graphics. So Danny was deep into graphic stuff and doing interesting graphics experiments over the network. And I was at DARPA by then trying to set up a program in packetized voice. And I needed somebody at ISI who would be willing to pick up the mantle and run with that as a program. Danny kind of found it really interesting because, well, it wasn't graphics, it was moving real-time video. I guess he probably, real-time speech, I guess he could also see video at the time being part of the mix. And so he went out there and got them into that. Well, it was very hard to do packet speech experiments. The ARPANET was a 50 kilobit network, and the typical speech compression devices that you could get either with chips or whatever tended to run like 64 kilobits. Pulse code modulation would take speech and code it into 8-bit samples 8,000 times a second. That was 64,000 bits a second. So it was more bandwidth for one speech call than the whole network could support. So it's clear even if you could figure out how to have one call, which we did by going to compression techniques, you couldn't have many calls at all. And so we thought about how to embellish that. And so I set up a capability using a wideband satellite system that we leased from DARPA. And these were fairly sizable dishes. I'm trying to recall the actual dimension. I would have guessed 6 meters in diameter. They were fairly big antennas. And I proposed to put one on the roof of the ISI building, which required the building owners to agree. And I had to be sure the roof was strong enough for it. These were heavy devices. It needed community and maybe county approval out there because people weren't sure the satellite dish wouldn't be an eyesore. And furthermore, California has a California Coastal Commission, which cares about how things look like from the water. And this was going to be visible from the water. And so we spent quite a bit of time working with all those groups. It was not only me, I spent some time, but mainly Keith and the folks out there, trying to convince them this was a good thing. And oh, by the way, this satellite dish would look good. It would be a symbol of high tech in the marina. And that's what eventually happened. The history of advances in the United States really relied on places that could invest in R&D with a view toward the future. I guess the last big enterprise we had that was like that was Bell Laboratories. That's long gone. When AT&T split up, the remnants of Bell Laboratories became more focused on, individual motivation of product groups. You really have a tremendous amount of money being put into research by industry. It's larger now than it's ever been in the past, much larger than it ever was when I was at DARPA. But all of those investments tend to be what I want to call the relatively short term. I don't mean next week, next month, or even next year necessarily, but where they can see a return on that research coming in the next 5 years, or maybe some might even go out a little further, that 10 years possibly. Nobody is looking at what you could do in the next 50 years, what the really long-term view would be. And so places like Bell Labs could afford to take that kind of long-term view. Places like an ISI could take that kind of a long-term view if somebody were willing to fund it, because they don't have products and services that they sell that's funding it, so they're dependent on places like DARPA, as would be a place like CNRI that I run. But in order to make this work, you need some place in the federal government, I believe, that understands the importance of that and is willing to sustain it. Now, places like DARPA are constantly changing, and so they may have had a big focus on networking back in the late 60s or 70s, they might look at it and say, look, industry knows all about that now. Let's focus on pharmaceuticals. And so there's not necessarily a continuation of support for those kind of things. And you might look at the universities and say, well, universities cope with that just fine. But the fact of the matter is the universities have a main flow of support that comes in. It comes in through, tuition at the students they pay. They have a very fundamental mission to educate students. It comes in from their graduates, the faculty who make donations, and that's quite a bit of their funding. And they get some from research. Now, the really good research places do much better than the ones that aren't so good at research for obvious reasons. But there's a constant turnover in those universities as people that are hired on one research project and the funding for that stops, they leave, maybe go to industry, and other people come in with new ideas. But they've got a mainstream source of support in either their alumni and their student bodies that are there. A place like ISI doesn't quite have that. So if somebody were to, endow it, with enough money that they could run it off the endowment, then I wouldn't be asking these questions. Eventually I became the director of the office that was funding all of this stuff. And in the run-up to that, it was very clear that we needed to do something to get the funding back to the point where it had been before the Vietnam War syndrome kicked in, because DARPA's funding dropped dramatically for research around 1973 or 4. And there was a lot of additional work that had to do with more like military test beds and things that didn't really resonate with the research community, but were important to defense. So I started a program in 1976 or 7. I started thinking about it in 76 to put VLSI architecture and design into the DARPA set of activities. I was motivated by a paper that Ivan Sutherland, Carver Mead, and Tom Everhart wrote, kind of pointing out that we're moving into the submicron domain, because everything in VLSI at that time was 4 and 5 microns. That's terribly big. It's like 1,000 times bigger than today. It was fairly large-scale dimensions. And so I set up a program at DARPA to fund the research community to work on, because I thought that the future of the research community in computer science really depended on getting involved at the architectural level and how computers are going to evolve. And that depended on VLSI. You no longer could think about designing computers effectively with large-scale vacuum tubes, certainly. Those are a thing of the past. But even transistors, you needed to pack a lot of computing power, which meant integration, and VLSI seemed like the only way that could go. I knew to have a program where we were funding researchers to do VLSI design, it's like writing computer programs when there are no computers to run the programs. It's an exercise in pure logic. I mean, maybe this program would run, but I have no computer to run it on. Well, if I design a VLSI chip and I can't fabricate it, I have no idea whether it's a good design, how it works, and whatever. So I needed to help the community to get these things implemented. Xerox PARC had decided to demonstrate how this might work. And they asked for permission from DARPA to run a class at MIT and ship the designs back to Xerox, and they would fabricate them locally. And I had to agree to that, which I did. It was very successful. But it's interesting that Lynn Conway, who was doing that, had worked with Carver Mead to document how to do design. They had a textbook which became sort of a standard in the field. Xerox Corporate decided this was not something Xerox was going to be able to capitalize on long term. It was a service to DARPA or to the community for a while, and they asked if we could find a place to do it in behalf of them. And so I approached Keith at the time, and I talked to Danny and asked them, would this be something ISI was interested? Keith was very enthusiastic. Danny was pretty enthusiastic as well, except that he didn't know much about VLSI design at the time, so it wasn't as neat a fit as working on Packet Speech was from his graphics work. But I arranged for Carver Mead to take Danny to Caltech and give him an office there. So he spent like 6 months there being trained by Carver in all of this stuff. He went back to ISI and set up the program. DARPA funded it. I was the point person on it because it was my program at DARPA. And my only contribution to that program was the I in Moses. Danny wanted to call it MOSES. I said it sounded a little too biblical for me because it stood for MOS Implementation System. And so that was how Moses got started. And DARPA made use of it throughout the whole period. We had the VLSI program in place. NSF later ended up putting some funding into it, and that activity is still ongoing at ISI to this day. I think it's, I don't know the details, but it's probably tens of millions of dollar effort, or it has been probably for quite a while. The thing that made it survive was, in my view, the ability to do those designs internationally as well as domestically. It wasn't clear that that was going to be a possibility in the early days because people were very worried about using VLSI for supercomputers and the chips could power them, but it clearly was apparent by the time of the late 70s that that wasn't really a reality, but took a while to really sink in. And so eventually it was approved, and I think that was a big help to ISI and to the Moses program. Let me begin by saying that of all of the challenges that we have in front of us, to me, as a technologist, nothing is more important than how we manage information. Why do people want to use machines? Why do they want to use the networks? It's all about accessing information. It's all about creating information and making it available. It's all about possibly entities interacting with each other to share entities, even if one of those two are not a human being. That's going to be with us forever. I don't see that going away. Given that that's the case, I've spent much of my time trying to understand how we should better manage information going forward. And there were three things that were very clear to me. One is that we need to structure this information in a form, I call them digital objects, that if one of these things showed up at a machine, the machine could figure out what it was. It just showed up. I mean, think about large data sets. Somebody sends a data set to your machine. Machine has no clue what's in there unless it knows what showed up and how it's structured and all that. So that's number one. Number two, if you want to find a piece of information, you would really like to do it in a persistent fashion. So, if you create a film, you can put it up on today's net. It's on an ISI machine. If somebody wants to get it 20 years from now, 50 years from now, 100 years from now, and you say, well, it was a file named such and such on a machine at ISI named such and such, but neither the machine or the file is still around, then what? You want to maintain something else that says, well, it was moved to this machine here and changed its name to that there. And so one of the ideas has to do with persistence, and I'll get to that in a second. Third has to do with ease of identification. So if you want to get something, you like to be able to find it somehow by not building into the identifier for this, the semantics of what it is. You can leave that to what are called metadata registries. But if somebody says, here's the identifier for that object, what do? Okay, so here it is. It's a string of bits. What do I do with it? You're probably not going to use any of the existing systems because this has got to survive for a long time. And so there's a means of resolving these identifiers to actually find it and to find it in a form that you can then parse it by machine. And you need ways to interface all these systems and to do it securely. People don't often like to deal with it, but I was worried especially about all of the potential cybersecurity kinds of concerns that we now have. how do you know that people are standing behind the information? I wanted to have a way of knowing who put these objects out so you could validate them, that you could deal with the internet in an anonymous fashion if you wanted to, but you might not be able to get much of what you're liking because nobody will let you into a bank account anonymously. No, they want to know who you are. And so you can use this digital object notion, to deal with the equivalent of, disseminating public keys, private keys. We already had a PKI infrastructure notion, but we didn't have a way of really disseminating them widely. Those are all important things to get done. I still think they are very important to get done. So that's a challenge from a technical perspective. I'd like to see the Internet of the future be dealing just with these digital objects. There are groups around the world I know that are refining it. Like they're saying, okay, if you have a digital object, you need to have these conditions apply to it, which we left open. The nice thing about an infrastructure is it's subtractive, not additive. Like a painting is additive. You put colors on, you add more colors, and eventually you get a painting. But with infrastructure, it's like sculpting out of marble. You take something away here, away something here, and you really want to end up with the minimal set of requirements that you need to provide that infrastructural capability. And then everything else is kind of an application of it. Now you can build on it over time if you see that every application needs a new function you didn't envision before. So that's what infrastructure is really all about, but it's going to take a while to get something like that out there. Having said that, there are all of these social questions. That's how you started your question. And, I am not a policy guru in the sense of knowing exactly what to do. I mean, I and then Vint and myself dealt with all of the early social things in the research community because we knew them pretty well. But when you deal with society as a whole, and a lot of it is dealt with by criminals, a lot of it is dealt with by, nation states that maybe don't have your interests at heart, I think it takes more sophisticated analysis and reasoning as to how to deal with it. I always felt like the way to deal with internal network threats was by using counterparts in the network to detect them and counteract them. So if something starts to happen, you can interact in microseconds, like antibodies in your body. Many years ago, Vint and I wrote a report on what we call it the world of nobots. We're talking about digital libraries, but the idea was you could program these mobile programs to move around the internet and carry out functions on your behalf. Today, we are still, for the most part, constrained to fingers on keyboards and eyeballs on screens, or maybe tapping on screens, or maybe blinking on screens, but it's essentially user-controlled. Not like we can say to these mobile programs, here's what you should be carrying out, here's what you should be looking for, here's what you should be defending against, and build that out into the world. We wrote that first report, 1987 or 8. It was right at the time that the very first real challenge on the internet showed up. It was called the Mars worm. And most of the companies who thought maybe this is a good idea said, we're not going to touch this because nobody is going to want a mobile program showing up on their machine that was written by somebody else and then executing on their machine. Now, you could argue that you use the same techniques to defend against bad things happening on your machine, but it really got put on the back burner. But maybe it's time to resurrect some of those ideas and move them forward as well. But there are serious issues. I mean, governments have been responding to them. Oftentimes they respond in ways that are pretty draconian, like unplug you from the net. Well, you need more fine-grained solutions. I mean, if somebody breaks into your house because you didn't have a lock on your door, well, maybe the right thing is put a lock on your door as opposed to a draconian solution like shut down the road system, right? So nobody could get to your house. I don't have any, societal solutions, and furthermore, anything I would suggest would be up for debate in every political forum you can imagine. In the U.S., it would be in the House and the Senate, it would be in the White House, it would be in industry. Even in the early days of the internet evolution, there was a president's National Infrastructure Advisory Committee And one of the things that was clearly on the agenda was what to do about security. And the administration was pushing solutions, and industry was saying, well, we have some different ideas, and they never could get convergence because they could never get everybody on the same page or even agree whose decision it had to be or should be. So I think we're going to be living with that in the future, and there are so many issues today that may or may not be affected by computers, computer science in the future, and we'll have the same set of issues. Who gets to decide? We wouldn't have the space program without computing. You wouldn't have today's cell phone technology without computing. You wouldn't have, a lot of the advanced computing research in this country without computing. A lot of the breakthroughs that have been made in different areas have come from simulation. People are now talking about making cities even smarter than they are, instrumenting the highways. Virtually every device in your home is going to be a smart device of some sort. We now have the Internet of Things. There are so many. The thing I would say is that there's been a recognition now that computing is so much applicable to just about everything we do, that it's the recognition that we now have the capability to apply it to almost everything and to think about those things in new ways. That was really been the biggest contribution. Most of the things I do day to day, some of them are based on applications of computing, like finding information on the internet. Today, most people would probably go to one of the search engines. That's a big computing activity in its own right. So our world is fundamentally enabled for change by the existence of computers and computer science.